us from Leuven after a master's in Belgium. For his time, though, interestingly, he spent during his master's a year in China at Tsinghua University, a year at Aachen. Wind turbines, I think. Yeah. Vertical axis. So he managed to spend most of his master's away from his home university in true international fashion. So he came to us then in 2014, started off as a TA, and then we started the Rebels project in 2014, and it's hard to believe it's been almost 4 years on Rebels. And now with a social person, so it was always fun to have Alexei at the new student recruiting, and as Lori Cisneros and others would say, well, just give him to Alexei because he knows everybody there. In any case, it's a great pleasure to see Alexei reach this point, and as you've read hopefully the announcement on Protonic ceramics, his work is really is multi-scale and is spread all the way from fundamental cell level activities to systems. So with that, well, let's welcome Alexei to the stage here.
So first of all, thank you, Rob, for that nice introduction. Thank you, Ryan. Thank to all of you to come and attend this wonderful day after four years or so, to share with you what I think I discovered and might help science go a few steps further to develop a new technology that might be the technology of the future, we hope, if not to find another one later on. So first off, I would really like to thank both Rob to be my advisor and then Sandrine as my co-advisor that supported me through the whole long path that's his PhD. So today we're going to talk about protonic ceramic fuel cells, and so my PhD especially was about trying to scale up, going from a cell and fundamentals of cell design all the way to a system that would be producing a few kilowatts of electricity. And so the title cells to system. So I hope some of you will learn what a protonic ceramic fuel cell is. Others will learn some more advanced results for their own research, maybe. So where did it all started? So as Rob just mentioned, so about 3 or 4 years ago, the Department of Energy was trying to fill a technology gap here that you have for small-scale distribution generation. So that means like small generators from 1 to 25 kilowatt. And the problem is that there is no cheap generator and there is no efficient generators. So the goal with the protonic ceramic is to really fill the gap with a efficient, 50% efficient and less than $1,500 per kilowatt generator. And that would bring us to our protonic ceramic fuel cell that is running at 500 degrees C, which for the ones that know what an SOFC is in the PEM, it's somewhere in between, so we're trying to take advantages from low and high temperature fuel cells. So the product in itself was divided into 3 subgroups. So the first task was led by Ryan's group and was looking mostly at optimal quarter-size cells that are as big as a quarter but produce about a watt, can make a small fan turn just by blowing some and put it into a stack, which was in the first PCFC stack made, or that's what Neil claims. So. So then the task I was part of and was led by Dr. Brown was mostly the system and the mental results going from a button cell scale to an actual kilowatt production system, and then try to feed back the results and the observation that we made back into the experimental groups, and to try to guide them in their own research and say, for us on the side of the customer. So for the ones that are not familiar with PCFC, so protonic ceramic fuel cells is a kind of material that allows the conductivity and the conduction both of oxide ions, so just as a normal SOFC, and then also protons that would be in a protonic SOFC. So our PCFC is a mixed conducting SOFC and basically conducts both oxide ions and hydrogen protons. And so once we go from a button cell towards a channel here, you see on the top side we have fuel going in and then air at the bottom. And so the methane is going to see where then you can have a car working in fuel cell maybe. On the cathode side, you have pretty nice button cells between 12 and 25 centimeters square, working with an neutral tech, and then kind of the scope of this project where we are and to the DOE to give us so many millions to work on in the last few years. So first utilization is SFC that could then dilute and have a lower fuel utilization. Any real numbers, so in this wide range of fuels that the fuel cell works on, name it limitation of that technology. So what is then contribution to the project? Because Ryan's team showed very high performances. My project was to try to figure out, then we also looked at this high turbulence in the models to predict what the 500, 550. Took 4 years to go from 3 centimeters crack at room temperature after the cell year. So there's a delta T of about 5. So in case you manage, you have no crack, and that is due to chemical expansion. Overall, my 2-3 years with stresses and try to that stress. And so we included in that mother side defect transport that allows. Then on the other side, the project forward trying to predict operation. And on the other side, we also looked at 2% electrical efficiency with natural gas, because nowadays we're trying to put thermal and crack after the fatigue. And as we just saw, that cracking, the second key step is when you sinter the down to room temperature, and then again the cathode crack, or it could bring more stresses inside the membrane. And then the third critical step is once you start operating the cell. So here we assume that at 700 C, when the anode is reducing from nickel oxide to nickel, the ductility of the nickel will release a residual stress, and so you break down to 550 C, and that's only at 150 degrees C delta T. So here the thermal stress won't be that important. And mostly the chemical stress due to the how do those thermal and chemical stresses come? So physically, how can you see grain of a PCFC is made out of BZY or zirconate on the left, and then you dope it with some yttrium, so you see on the right side. And so when that material is in contact with steam here, and so here we have the chemical reaction, and so how it looks like, you have the lattice parameter. And the lattice parameter is basically the side length of the cube. And you see that line, and then you see that this lattice parameter expanded because of the incorporation of protons. So it ranges of those different phenomena. So on one side, you have the maximal chemical strain would be about 1.4%, so it's about 10 times higher. But still, usually the problem is not to have a convection with the same delta T. We understand the physics now. We first need to gather new and recent technologies. So we need to gather material properties both for solid mechanics, the Nernst-Poisson that Bob Poyong and others have been working on. And so once we combine all those, there's going to be some iteration here where the from solid mechanics will feed back into the Nernst-Poisson model. And so trying to figure out how are the defects going to move and what are the different phenomena that are going to make the diffusion term that is basically dry term, where basically the defects are going to be moving based on the charge defects towards the other side. Then the third term that I added into that model was defects on one side or the other. So if you have a very high stress on one side because there's so many protons, but now to derive this hydrostatic stress, we have to look at the conservation of stress. And the next term here, this would be the chemical stress due to chemical expansion. The stress tensor triangle matrix by 3, and you get to the hydrostatic stress, which is fed back into the Nernst-Poisson. Assume that there is a thermodynamic equilibrium at the surface of the membrane, just to the defects inside the lattice. We have a sealant. In fabrication, we assume that the cell is free to move at the bottom. And so that way we're trying to with experimental data. So when we look at this little cookie here, which is the anode and the electrolyte, and then we cool it down to root megapascal. And so, and that 80 megapascal is here really at the interface between the anode and the electrolyte. So how is that maximum tensile stress gonna vary, and why are we looking at the tensile? Very often they almost never break under compressive stress. And so here the maximum tensile stress is at 80 megapascal, and then the three big, and at the baseline the electrolyte is a CT of 10, and so that's a pretty big difference between both CTs. And so once you increase the CT of the electrolyte, you decrease the CT mismatch, and so the delta T of 1500 is going to have a much 20 megapascal, so that's a huge difference. Redistribute the stress over a larger amount of material and active for electrochemical performances. So once we look at the second step where we add the cat, we see that basically the same phenomena counts where we see again that the CT of the electrolyte is the biggest driver for those tensile, and those PCFC can just play and make the cathode they really want to make. It's not going to matter much. If you look at the third step, and the third critical steps, once you're going to actually operate the fuel cell at 550 degrees C, we see now that the stress is going from 80 now more about 40 megapascal. So it's about half. The temperature is now at 700, and you're only cooling it by 150 degrees C, so your delta T is 10 times smaller. Charge within the anode is basically going to decide how much porosity there is in the anode, and the more porous the anode is, so on the left side, the more flexible it will be. And so again, but then important here is to look at the third parameter, which is the electrolyte CCE, which is this coefficient we looked at, because there is quite a bit of difference, and about 10 megapascal difference between points difference that should be looked at in the future. So at the anode electrolyte interface and 36% on the other side, and that is assuming a BZY20 chemical expansion of 0.033. So how does the tensile stress relate to actual fracture of your cell? So one, the fracture toughness, so having a stress here which is sigma, and then the fracture toughness is 138 megapascal per, and that should be a square root of meter. That comes from Håkas Sasinas from NTNU in Norway, and they measure properties, and so we are trying to derive what this AC variable is, which is the critical flow size at which your cell is going to break. And so here when we look at the electrolyte CTE at the bottom, so when we vary from 8 during fabrication, and the reason is because during fabrication your delta T is about 1500, changing the CTE is not going to change anything about tensile stress. So during operation now, when we vary this chemical expansion coefficient, we see that the BZY10 coefficient is here about 0.15, and coefficient for BZY20 is about twice the guy. It would be great to work on the BZY10, but you have to know that BZY. So the idea would be to analysis how this is going to, how much is in process, and hopefully around it, and we'll be able to compare our predictions with those actual part. Look at the system, and we try to predict how this whole system, looking at efficiency, but also operation cost. So is it more expensive? So how is a PCFC actually made? Those materials allow to basically prepare the powder and sinter, preparation of the powder as well as the sintering application of the process. And we also only have one steps would be for our PCFC, and then another 3 sintering steps for each layer application. And so that makes the numbers, we came to a very attractive conclusion, even though it's just a prediction and estimation. We are very happy to share that today, that showing that even though a PCFC running at 500 C with 150 megawatts, milliwatts C, it means that your PCFC here on the left side needs to produce twice the amount of cells. It needs to produce 2 times more cells, but it's about half the cost supporting previous observations. So now, once we put this cell into a full stack, so the whole stack, and so here we see that working at a lower operating temperature allows us to reach also attract a temperature of 500, 550 as compared to SLC that is running at 800, and allow us to be competitive also for current collectors and interconnects. So when we look now at this, you can see that we need about 2 times more cells, so we need 2 times more seals because there's no other lower temperature seals that have been reported now in the literature. Directly driven by power densities, which is also directly related to temperature of this increase in power density. So that's a significant observation. So this stack here that is running under methane, and then this is just going to invert the electricity from direct to an alternate current on the power grid. So we need to feed it with methane, and then first we have the methane that's going to rise the pressure to go over. So natural gas is very nice, but it's also to allow for steam methane through the membrane. And then you're going to preheat that, and then it's going to get to the PCFC stack. You're going to preheat it again, and then you're coming to, it's going to electrochemically burn and produce more heat and the air coming into the system. And then because we want to have a water neutral system, we also need to extract a given amount of water using a condensed out while your system is running. Electrical efficiency. And so this is running at 0.8 volts, 85% utilization, so a channel to prevent any crack in the channel, to prevent coking, but here we just start at 2.3 steam to power ratio, and then increase your electrical efficiency by almost 10-12%, and so once you combine each a value of about 72.4% electrical efficiency, those lower temperature of 550, still performance with a cell and stack that is here. We're going to look at like a high 5 years. So basically, cost that you're given for to account for high temperatures, and you also $10. Now cheaper it's going to become, and then finally, so annualize that system and using interest rates, and then we have going to run full time at full power because it's not going to run all the time at full. You need to we take all that into account in the cost, analyze system cost with the fuel cost, analyze cost of electricity, and so that's the it's also in cent per kilowatt hours to Excel Energy, which that's without the markup, the money you could make on top. Overall PCFC system, we see that the stack to allow and to account for stack performance by over 20%. Then the inverter is a pretty big amount of cost. The inverter capacity, the power capacity of your system, $1,052 once you increase the cell temperature. And the reason here is because you have a big voltage. So cell voltage is your compressors and blowers is much lower. So again, pretty significant and needed. So the smaller your air blower could be. The operating cost, which is this LCOE in cents per kilowatt hour, but by only 4%. So it's not an important contribution. And so that's was okay. It's great to cost this. Like what application we looked at. So our efficiency can get the small backup generators initial cost because they the lowest cost for all of us. You're going to Utah, it's too much and LCOE. Of those costs is a high electrical efficiency. Our within LC costs we are trying to now I would like to the development should look at the oil that when you add porosity because the phase boundaries a long way before we cathode that would allow cost was directly makes you just want a different cost because it's still then the system that tries at 70% elevation. Then the cell voltage is a trade-off between cathode and the temperature of the cell because the temperature of the cell will increase the power density and your temperature rise over the cathode. Cathode is related to your stress, and so that's for further study to figure out what the maximum delta T gradient over your cell is and will be documented. So I've reported the stack cost analysis in a publication a year ago, and then I thanks to Dr. Berger in Chicago about my stress model, and then I gave a keynote, invited talk in Bordeaux about my. With this, I would like to my 4 years of research. Then I also would like to thank quickly Castra and all the best with their future research. And then thank all the last few years.
Questions from the audience. So if there are
that they show that when they had 80% nickel, it would break, and so I could back calculate that at a given flow size it would break, but they didn't report the flow size at which it did break. So
the numbers seem pretty high, so there seems like there's a lot of hope for getting to lower flow sizes.
Yep. Thank you.
Oh, what about the cathode makes it so expensive? You know?
Yeah, so it's because so the cathode material itself is very cheap, but then the manufacturing of that cathode is very expensive because if you want more detail, you can ask Protonic, but basically we have a sol gel method first. So first you have to calcinate the cathode, then you have to dry it, then you have to bubble it, then you can apply it as a screen printing, and then you have to heat up again and sinterate at 900, and so that's what makes it more expensive than the anode and electrolyte together.
other questions? This is your chance. There we go.
Okay, so I'm sure you didn't have to cover that much because it was already too many studies. But I wonder if your current model, can you include a Koch layer to understand the brutality of the material? Because when Koch happens, forms, it not only kills your surface area, it also brings the stress into the material to make it more brittle. Just for future reference, can we add a Koch layer to your current model?
Yes, we could add a Koch layer. So basically, I'm working in COMSOL, so we could change the characteristic of the first 10 microns on the anode side and say that the Young's modulus and the CT is changing because of that extra Koch that might block the pores and so on. So yeah, thank you.
On the stress models, when you were doing the temperature gradients, was there any like 1500 to room temperature? Did you what type of gradient did you use in the
Just slow down. So we assume here in those models we assume just steady state. So we don't look at the transient temperature change. So we just assume okay we are now at room temperature, and so we see what would be the gradient. But that's another study. Yes.
Back to Jean's point, if the objective is to not have Koch, why would you want to model it? Because you think it's present even though we're saying it's not?
No, it is coaching. Doesn't matter how little, but by time it's accumulating coal. Although you may not see the catalytic effect directly, but if you look at the industrial scales, one of the biggest problems is over years it becomes brittle. It's still catalytically active, but it's brittle. So you cannot regenerate brittle material. You have to replace it. So you didn't see when you studied the drying too, you see it's very stable, but over the time it's gonna get brittle. And the whole point is, from my question, at which level do you think that it's now gonna get brittle? Maybe it has more advantages with the PCFC than the aluminum or cordierite material that you choose. Maybe it's a selling point for your material actually.
Yeah, so it's a lifetime model.
It's a lifetime
degradation model.
Cost stability and so on, but I think it has a merit to study more.
Yep.
Okay, if there's no further questions, then this ends the public portion of Alexei's PhD defense.
Thanks for
Thank
coming.
you all for your attendance.